Okay, so good afternoon. It's a real pleasure to be here. So my name is Shobhana Narasimhan, and I'm going to talk to you about making materials on the computer. So I divided my talk into 3 parts. I thought I'd start by telling you a little bit about myself. Then I'll talk about computation and density functional theory, which is the technique I use. So I'll tell you about why you do computation, why one uses this technique called density functional theory, what it is. And then I will give you a few examples of work from my group. So a little bit about myself. So I thought, since this is a workshop for women in physics, I would start by telling you a little bit about my maternal lineage, because I think it's an interesting example of how life has changed for women in the last century or so. So the first picture is of my great-grandmother, Lakshmi, and she got married when she was 8 years old, and she didn't really want to get married. She was running around and playing. And so her mother-in-law-to-be came up to her and said, "If you come and sit down inside the room, I'll give you a mango." And she liked mangoes very much, so she stopped playing and she came and sat down, and then she got married. Now, usually, though it was common for girls to get married at that age, they weren't taken to the husband's house until they achieved puberty. But in her case, her mother-in-law had always wanted to raise a girl child, and so she took her right after the wedding. So after the age of 8, she almost never again saw her own mother. And she grew up to be a very talented musician. And that in those days, it was considered slightly scandalous for women to sing and to learn music from men and to sing in front of men, etc. And she wrote some very rare musical compositions. And it's also interesting, I think, to know when she wrote them, because she was kept always very, very busy with housework, raising children, cooking, etc. But as you may know, in many communities, there's this tradition that when a woman has her period, those few days she's sequestered. She has to sit in a room by herself. So this was practiced in our family at that time. So those few days were the only rest she got from the housework, and that is when she wrote these compositions which have now come down in our family. Next is my grandmother, Sugandha. So she got married after finishing high school, and she was about 18 years old when she got married, which was considered very late at that time. And it was an arranged marriage, and my grandfather had only seen a photograph of her and agreed to marry her. And then when he actually saw her at the marriage ceremony, he said, "She doesn't look like a photograph and I'm not going to marry her." And then there was a big scandal, and then he had to be coaxed to marry her, etc. And after her marriage, and after having children, she went on to study for a bachelor's and a master's. And she had a master's in Hindi, and she is also a very good musician. And she went on to set up a music school. Next is my mother, Shakuntala, who's still alive. And she's a very well-known journalist and musician also. So she was doing her PhD when she got married. And she was about 23 when she got married. She was doing her PhD in economics. But about a year after she got married, I was born. And then she found it very hard to continue with her PhD because she had to look after me, etc. And so she couldn't finish her PhD, which was something she was very sad about. But then she was able to sing. But then when I was a few years old, she mysteriously lost her voice. Okay, and the doctors couldn't figure out why. And I have very early memories of her whispering to me because that's all she could do. And then she was so frustrated, she didn't know what to do. So she started writing because that was the only thing she could do. And then she actually became very well known as a writer. And she became a well-known journalist. She won many awards. She had columns in newspapers, etc. She also got a voice back, and then she was very well known both as a musician and as a writer. And after I got my PhD, I said, Amma, now I've got my PhD, your turn. And then she, at that age, she went on to get 2 PhDs, one in music and one in women's studies. I'll tell her that you clap. And that is, of course, me. I didn't get married by choice. I decided I didn't want to get married. I have a PhD. And you will hear more about me. So this is about my father. So that is my father as a young kid, very traditional South Indian Brahmin boy. His head was shaved. He had this top knot at the back, diamond earrings. But then when he was about 12, my grandfather died. And so the family was financially in difficulties. And then he went on to study mathematics. And I learned only a few years ago that, for example, he did his PhD in TIFR in Bombay in mathematics, and he was one of the first students to get a PhD from TIFR. But when he got called for the interview for the PhD admission, he didn't have enough money for the train fare from Chennai to Mumbai. And so one of his teachers heard about it and lent him the money for the train fare. And when he got his first stipend, he paid it back. So by the way, that's me with him. He went on to become a really very well-known, internationally known mathematician. And here I just put 2 tweets about when my father passed away a few years back. The top one is from Ed Witten. How many of you have heard of Ed Witten? Okay, a few have. Ed Witten is possibly the best known physicist in the world right now. So at least now you've heard of him. And the second person, okay, you know who that is. Okay. So my academic trajectory, I grew up in what was then called Bombay. So I went to school and college there. Incidentally, I really hated physics in school. I didn't have a very good teacher the way we were taught. We just had to memorize things. Her way of teaching was, okay, this is Boyle's law. You say what is Boyle's law and then what's Boyle's law? What's Boyle's law? What's Boyle's law? What's Boyle's law? If you get one word wrong, out of the class. So I really hated physics. I cried both before and after my ICSE physics exam. I never dreamt I would become a physicist. So after my MSc at IIT Bombay, I went to Harvard University in the US for my PhD. Then I was a postdoc at Brookhaven National Lab. Then I did a second postdoc at the Fritz Haber Institute in Berlin. And then I came to the Jawaharlal Nehru Center for Advanced Scientific Research here in Bangalore, where I've been ever since. So this is some pictures of our institute. This is one of the computers we use. This is my group a few years ago. Now, we've been told that when we go from our institute somewhere else, we're supposed to boast about our institute a little bit, so I'm going to do that now. So this is 2019, when Nature ranked institutes and universities worldwide, and it normalized it by the size. So because obviously if you have fewer faculty members, you're going to produce fewer papers. So this is the world rankings, and here's our institute, and we came 7th in the world, and we were pleasantly surprised, especially given that Princeton University was 10th, Stanford was 11th, MIT was 12th, etc. Okay, so now you know about JNC. This is a recent picture of my group. 2 of my students are here. Sejal joined so recently that I still don't have a picture of her. I believe very strongly in mentoring women in physics, and I've been involved a lot with that. So one thing I've been doing for 11 years now is I've been organizing workshops for women in physics from all over the world, really. So this is one of those workshops that I organized in Trieste in Italy. That's me over there. So women from about 80 countries have attended these workshops so far. And I also go often to Africa to teach physics. And this is me that's me there with two of my African mentees. That's Anne-Justine Etindele from Cameroon, and that's Vinnie Mulva from Kenya. And they both learned physics from me, and they both now have faculty positions in their countries. So what do I enjoy besides physics? I mean, they're a bit geeky, the things I enjoy, but still I like reading, writing. I not only solve crosswords, but I set crosswords with a friend. They mostly have a scientific theme, but not completely. I like painting, so this is a drawing I did of my grandmother. I like to visit museums, I like to cook, I bake, I sew, I like traveling. So this is a picture of me with some of my students in Paris. I like hanging out with friends. Okay, so that's about me. Now I will tell you about computation and density functional theory. So materials are what I work on, and materials are considered so important, such a strong symbol of human civilization that we name the different stages in human civilization by the new material that they started using at that time. Okay, so you have the Stone Age, you have the Copper Age, you have the Bronze Age, you have the Iron Age, etc. And some of my students told me I have to put this smiling face there, otherwise you won't notice this iron here and understand why it's a joke about the Iron Age. Now, of all these, the age that fascinates me the most is the Bronze Age. Can anyone guess why? Can you guess why, as a sort of material scientist, the Bronze Age might be most fascinating? It's an alloy, and yeah, so you have to make it. It doesn't exist in nature. It means stone exists, iron exists, copper exists, but for copper, for bronze, you have to mix together copper and tin, and then you get a superior material. And it really fascinates me to think how they knew to do it, all those tens of thousands of years ago. So this is, of course, the periodic table. And we have about 98 naturally occurring elements. And we have about 4,000 naturally occurring minerals. But of course, we are not restricted to those. We can make new minerals. So as you can sort of tell, I think that out of these Lego blocks, this is a periodic table, okay? And the elements of the periodic table for us are the building blocks out of which we make new materials, okay? So we want to mix them together in different proportions, in different structures, and get new materials. So how many can we make? Okay, before I go to that, I just wanted to talk about bronze. I think I already told you this. Sorry, so this is some Bronze Age weapons from India, and this is the famous dancing girl of Mohenjo-daro. I had to study it in my history class. I don't know if you did too. She's about this tall, and she's made of bronze. Okay, so before the internet came, when I was a postdoc, for example, if we wanted to know what were all the materials that people had made, we had to look at these series of books called the Landolt-Bernstein series, and there would be book after book after book in the library. Now, of course, it's on the internet, but people have tried to estimate how many can potentially be made. So if you say that you have maybe 9,000 possible crystal structures, Then if you have a quaternary compound, that is a compound made of 4 different elements, they've sort of tried to estimate how many possibilities are there, and they think they're of the order of 10 to the power 11. And if you have quinary, that is you have 5 different elements, then it goes up to about 10 to 13. Now, this is a huge space to explore. Okay, you can't really hope to do it in some random way. So we have to find some organized way of doing this. So how did people go about it once upon a time? So first I want to ask you what you feel was the most important discovery of the 20th century. That's not the current century, but the previous one. So what are your ideas? Tell me some of them.
The transistor.
The transistor is a very good suggestion, yes. Anything else? The flight, the plane.
Radio.
Radio, okay. World Wide Web, okay. So what are the things that you think totally transformed human life? I mean, there were many, many things that happened. Huh?
Like in general, whatever enhanced communication.
Okay. What about health? Huh? Yeah. Sorry, what? X-rays. Okay, so X-rays certainly, do you think X-rays are the most important thing? It was certainly important. So the question is, what is the most important? Different people have different ideas. But, okay, you all are physicists, not chemists, but still many people, not just chemists, think that the most important discovery was the Haber-Bosch process. Now, I presume that though you are physicists, you have studied the Haber-Bosch process. How many of you know what the Haber-Bosch process is? Okay, so quite a few of you. Okay, so this is a process for making ammonia by combining nitrogen and hydrogen. So this was this article in Nature in 1999 when they were trying to decide what was the most important discovery of that century. And this article argued, sorry, oops, what am I doing? Yeah, you're seeing all my jokes too early. That the Haber-Bosch process was the most important scientific discovery of that century. So why is that? Because it was because of the Haber-Bosch process that we could make nitrogen-based fertilizers, artificial fertilizers, and that enabled us to increase our food production enormously, and therefore we were able to sustain the growth in population. So what this graph shows is versus the year, okay, this shows how much the world population grew, and this shows how much of that population could be supported if we didn't have these synthetic fertilizers. So we are able to support this additional amount only because of synthetic fertilizers and the Haber-Bosch process. Of course, you can argue about whether it's good or bad that we have such a large population, but it certainly made a big difference to human life. So this animation shows you the Haber-Bosch process. And okay, so let me wait till it circles again. So you have nitrogen atoms and nitrogen molecules, hydrogen molecules, they come and sit on this catalyst. The bonds break within the nitrogen, within the hydrogen. They recombine, form ammonia, and that leaves, okay? Now, the important thing here is that this happens easily only if you have this catalyst over here. So the question is, what catalyst? Okay, how do you know what catalyst to use? So what Haber did was he tried about 2,500 different catalysts, okay, before he found the one that we use today, which is iron. It's interesting to know that iron is not the best. Of the ones he tried, osmium was the best, but osmium is a very rare element, so you can't really use it commercially. So he decided iron is the best. In later work, people found out that ruthenium is even better. And then in the kind of work I'm talking about, where people have tried to make materials on the computer, people have found that a molybdenum cobalt alloy will be even better. So some people are trying to switch to that. But how did, I mean, this is just like a brute force thing. You just try and try and try and try. And by now, by today, it is estimated that 250,000 different materials have been tried as catalysts for this. But this is not a very intelligent way to go about it. So up to now, most materials we used were developed by trial and error or brute force. But now we're trying to do what's called rational materials design, where I'll explain to you what that is. And for that, you need to have a back and forth between theory and experiment. So now I want to ask you all again, how many of you prefer theory? Nobody? Okay, I'll ask you that too. How many prefer experiment? Quite a few. Okay, how many prefer to do both equally? Quite a lot. Okay, so now, so it's sort of equal. Okay, you'll realize in a second why I asked you, because I'm going to talk about theory versus experiment in physics. So it's traditional to have a lot of joking, cursing between the two groups. So here is this comic where, a theorist is saying, you experimentalists are inferior, you're just a bunch of stamp collectors. It is not an uncommon view, even today, I can tell you. And then the experimentalists say, what do the theorists do? That is so great. So as examples of these two, I put in two quotations. So this I found very funny. It's an experimentalist, Leon Lederman, who was a high energy physicist. And what he said about theorists is, a theoretical physicist can spend his entire lifetime missing the intellectual challenge of experimental work. I put that in a different color just because theorists would claim that there's no intellectual work in experiment. Experiencing none of the thrills and dangers, the overhead crane with its 10-ton load, the flashing skull and crossbones and danger, radioactivity science, a theorist's only real hazard is stabbing himself with a pencil while attacking a bug that crawls out of his calculation. Okay, so that's an experimentalist making fun of theorists. And of course, for theorists making fun of experimentalists, I put Sheldon Cooper. Okay. So, but recently, within the last year, I read a book that I want to tell you about. So this is this book called Love Theoretically. Has anyone here read it? Oh, quite a few of you have read it. Okay. So I don't think it's a great book. It's in the genre called chick lit, very disparagingly, but I think it's a fun book. And I'll read this from the back cover first. It says, Jack Smith, so the heroine is, she's a theoretical physicist, and the hero is Jack Smith, and it says, Jack Smith, the annoyingly attractive and arrogant older brother of her favorite client. Now, you may wonder why a theoretical physicist has a client, but we'll not go into that. Turns out to be the cold-hearted experimental physicist who undermined the reputation of theorists everywhere. And he's the same Jack Smith who rules over the physics department at MIT. And will falling into an experimentalist orbit finally tempt her to put her most guarded theories on love into practice. So this is actually a best-selling book. And a lot of it is about experimentalists versus theorists. But in the end, of course, the two are reconciled and they fall in love and they get together. So I'm a computational physicist, so I don't do much of pen and paper. I do some. I don't do any experiments at all. I do some pen and paper, but mostly what I do is computation. So why do we do computation? Okay, so it is much cheaper to do something on the computer than in a lab. It is, okay, I put can work from home partly as a joke, but believe me, when the pandemic was on and when the lockdowns were in place, it was something we really appreciated, that we could work from home, which the experimentalists couldn't do. I have also found that, for example, I had a postdoc in my group, and she was the mother of two very young kids. And she found it very hard to combine that with being an experimental physicist. And she switched careers, switched fields to being a computational physicist, because then she could work more easily from home. Okay. It's often quicker. An experiment can take very, very long to do, but the calculation is easier, quicker. It can lead to greater understanding. Now, I've written you can easily simulate conditions that can be hard to simulate in a lab. For example, supposing you want to know what is happening to the Earth, to the iron at the center of the Earth, or the methane at the center of Jupiter. These are subject to very, very high pressures. Okay? There's been a suggestion that the methane at the center of Jupiter actually forms one gigantic diamond. Okay? But you can't test that in the lab because you can't achieve that kind of pressure in a lab. But in a calculation, on a computer, it isn't really that much harder to subject your atoms to a higher pressure than a lower pressure. So this is something you can do easily on a computer. We can switch off effects, which is something we do quite often. For example, if we're seeing that a material has some properties and we want to know, is it because of the electron spin that it has this? Or is it because of relativistic effects that it has this property? In our computation, we can say, okay, the electrons now have no spin. Or we can say, I'm not doing a relativistic, I'm not solving a relativistic equation. Okay? But you can't do that in the lab. And we can make predictions for experimentalists to verify. But all this has become possible only in recent decades, because if you're going to say a computation can replace an experiment, then you have to have a way of doing computation that is really, really accurate and that can really replace an experiment. Okay, so I'm going to tell you about that now. Yeah, sure. To do the experiment. Yes, that's true. Yeah, so that's what Leon Lederman was saying, right? He was saying that the experimentalists face real danger, whereas we only risk. So initially, he said stabbing ourselves with a pencil. I guess now it is like, I don't know, breaking a nail on the keyboard or something. Yeah. What is the difference? Okay, so an experimentalist will actually, I mean, to me, it seems so obvious, I don't even know where to start. Okay, let me give an example. Okay, supposing you have a superconductor. You have a material and you want to check whether it's a superconductor. The experimentalist will actually take that material into the lab, change the temperature, measure the conductivity, and see if the conductivity changes and is it a superconductor. Okay, a computational physicist will instead simulate that material by writing equations, which I will show you soon, on the computer, so that you are simulating how that material will behave, and you do the same kind of thing. You change the temperature, etc. See if you see this change in properties. A pen and paper theorist would instead probably simplify it by not tackling the full complexity of the problem, but take some key parameters which they believe are important for describing the superconductivity. And then within that model, they will see whether they can see the superconductivity. Is that helpful or not?
Experimental physicist can be like, there's gray area.
I mean, why can't the experimentalist also do the theory or the computation?
Computational physicist, like, you cannot define nowadays difference between them, because every experimental physicist use computational, like computation, to do their work, calculations and everything.
Not really. I mean, certainly they use computers to help record their data, etc., but not necessarily to do the simulation. It is true that for many of the simulations, the codes are becoming more user-friendly, and so there are packages where you can just sort of, with a few mouse clicks, you can do the simulation. But I would say that all of these techniques are still, whether it be the experiment or the simulation or the theory, they are hard enough and complex enough and need enough training and experience that typically people specialize in one of these. But of course, there are people who do more than one of them. But see, I often get PhD students coming and saying, I don't want to choose between experiment and theory. I want to do both. I don't generally recommend that. I think that at the early stage, it is better to pick one and learn to do it really, really well. And then after that, if you want, you can learn the other. Okay. Now, of course, the way it usually goes is it's usually an experimentalist who learns the experimental techniques and then learns how to do the simulation. It's very rare for someone who's a theorist who then learns to do experiment, but that also exists. I mean, there are people I know who've done that. Any other question? Yeah. Yeah. Yes, yes. So you can't, I mean, that is to learn, that's to gain an understanding. If you learn, for example, that the relativistic effect, which is the spin orbit interaction, for example, is important in order to have that property, then that gives you some insight. For example, it may tell you that, okay, I should only use heavy elements if I want to have this property. So it is not that I'm saying in the real material, I can switch off the relativistic effect or whatever. It is a way to get greater understanding, which is possible within a computation, but is not possible typically in an experiment. Anything else? Yes. No, I believe it is still a controversial issue. Yes, so I believe that, okay, so this is not my area of expertise, so I've only read like, the articles in Nature or Scientific American or whatever. But if you're curious about that, I have a friend who works on this particular problem. So I can put you in touch with him. I also don't know, how many of you here have heard about the Science Gallery? Okay, very few. So the Science Gallery is a museum in Bangalore. It's free, and it uses art to convey things about science. So it's not like a standard science museum where you just have working models of things. It has all kinds of strange, I mean, I won't take too much time now to talk about it, but it's a very interesting place. And right now they have an exhibition called Carbon, which is all about carbon. So I've been telling them to invite this friend of mine who works on whether the methane becomes a large diamond to come and talk about that at the Science Gallery. And they call it Diamonds in the Sky is the name of his talk. So anything? Okay, I think I'll continue. Yeah, is it okay? But if you have any time, go see the Science Gallery. It's fun. It's closed on Mondays and Tuesdays. Okay, so what is the basic physics problem that we're trying to solve when you're looking at a material? Okay, So you have some number of nuclei, okay, which have some atomic numbers and some positions, and you have some number of electrons at some positions, and these interact via the Coulomb interaction. I guess everyone here knows what's the Coulomb interaction, okay? And examples of such systems are atoms, molecules, condensed matter systems. And how many of you here know the Schrödinger equation? Okay, nearly everyone knows the Schrödinger equation. So just like Newton's equations are the fundamental equations of classical physics or Maxwell's equations, the Schrödinger equation is the fundamental equation of quantum physics, at least at the non-relativistic level. And so this is the equation that one writes down. It says this is the Hamiltonian, this is the many particle Schrödinger equation, this is the energy, and there's this other thing that I think I'm going to skip, that the solutions must be anti-symmetrized to satisfy the Pauli exclusion principle. I'm going to skip that. The point is, it's very easy to write down this equation. It's very difficult to solve. So let me try to explain to you why. So, you know, in classical physics, for example, you have two body problems. For example, you can have the Earth going around the sun, or you can have the hydrogen atom where you have a single electron going around a proton. Okay? So these are things for which we can find exact analytical solutions. Okay? For the Earth going around the sun, we have Kepler's laws. You can find the trajectory. Okay? And for the electron going around the hydrogen atom, you can solve it at different levels of complexity, but if you have had a quantum mechanics course, then you have probably solved this problem analytically, the Schrödinger equation. This is possible because there are two body problems and therefore simple. If you have a three-body problem, it's only three bodies, but it's already much harder, as you probably heard. So a possible example of a three-body problem is the Earth and the moon and the sun, or here, the helium atom, or here, I don't know how many of you, can anyone recognize where this picture is from? Yes, tell me. Yes, Star Wars. Not Star, you must never confuse Star Trek and Star Wars. That is a great crime, okay? Yeah, so this is the moon Tatooine. This is the planet Tatooine, which has two suns. Okay, and a planet in a system with two suns, it's very hard to find a stable orbit actually. Okay, so these are all three-body problems which we can sort of solve numerically, but they're much harder to solve. Okay, so now, I mean, this is a horrible picture which many of my friends don't like, but I just made it to say we have lots of nuclei, electrons, etc. And typically, like, okay, say this pointer. How many nuclei and electrons do I have in it? Many, yes. How many? I'm sure you know an order of magnitude because you know a number that tells you that. Avogadro's number, yeah. So it's of the order of 10 power 23. Okay, and they're all interacting with each other via the Coulomb interaction. So it's really, really hard to solve this. Okay, so it's basically impossible. So this was summarized by Dirac. How many of you have heard of Dirac? Okay, everyone, okay. So he said the underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations that are much too complicated to be soluble. Okay, so we can write the equation, we can't solve it. So now we come to density functional theory, and how does density functional theory attack this many electron problem? Okay, many body problem. So I'm going to give you an analogy now because instead of going through the maths, the analogy is a little bit silly, but I think it is still instructive. Okay? So supposing I have a group of men and women, you can think of the men, if you want, as nuclei and the women as electrons, and they have complicated interactions between each other. Okay? I have been careful to maintain the fact that like charges repel and unlike charges attract, but the strengths are different. So now the problem I've given you is that you have to arrange them, move them around so that you achieve globally the highest level of happiness. Okay? So this is obviously kind of hard to do. So in the same way, if you have nuclei and electrons, we're supposed to move them around till we reach the lowest energy solution. And it's hard to do. Now, what this physicist called Walter Kohn did was that he showed you can map this problem onto another problem where you still have these nuclei, but you only have one woman. And you have to decide where to put her. So he mapped the many electron problem onto a one electron problem, which is obviously much easier to solve. But the amazing thing he showed was that this is in principle, an exact mapping. That the solution to this is exactly the same as the solution to this. Okay? Now, you obviously have to pay some price for this. It can't be that easy. And the complication comes from the fact that he showed that such a mapping exists, but he couldn't tell us what the mapping is. Now you may think, okay, big deal, what's the use of that? Then what are you doing? I mean, the reason we can actually work in a field called density functional theory is that we have very, very good guesses for what this mapping is. Okay? And what this mapping, the price we pay for this mapping is that it introduces an extra term in the Hamiltonian, if you know what the Hamiltonian is. That's called the exchange correlation energy, which I have sort of symbolically shown by putting face masks on the guys. The reason I used face masks because I first made this slide during the pandemic. And so what we know is that if we put the right face masks on the guys and then compute what effect the face mask has on the woman, the solution is the same for both. But we don't know what the right face mask is, so we have to design the right face mask. And we don't yet have a solution for this. We have very good guesses, we don't have an exact solution. So this is a challenge to your generation. If you can find this exact mapping, you're pretty much guaranteed to get a Nobel Prize. Okay? So this is Walter Kohn as a young boy. This is him getting the Nobel Prize for inventing density functional theory. So he has a very fascinating personal history also. He grew up in Austria. He was Jewish. So when he was a young boy, I think 13 or 14 or something, that's when the Nazis came to power. And so they organized what were called Kindertransport, where they took, they means not the Nazis, the people opposing the Nazis, they organized these train journeys from Austria and Germany to the UK, where Jewish children were taken away to keep them safe from the Nazis. So he and his sister were taken away and moved to the UK. His parents stayed behind and they were both killed in concentration camps. But then the Second World War broke out, and then because he was an Austrian citizen, he was considered an enemy alien and he was put in a prison camp. First in the UK and then in Canada. But that is the period during which he first got interested in science. And in this prison camp, there were many older men who were scientists, and they taught him chemistry and mathematics and physics. And that's how he got interested in physics, and that's how he became a physicist. Okay, so DFT calculations are also called first principles or ab initio calculations. The reason is the only input into your calculation is atomic numbers and atomic masses. So I want to tell you that this is quite a remarkable thing, because usually when people used to do calculations, they will take some experimental input, and then using that experimental observation, they will try to calculate something else. Like, for example, you may know the bulk modulus of a solid, and using your known answer for the bulk modulus, you may try to calculate the vibrational frequencies of atoms in that solid or something like that. Here, we don't do that. There's no experimental input at all, except for atomic masses and atomic numbers. And then you churn through the whole machinery of the calculation, and you get this remarkably accurate output. So now I told you about rational materials design. So what is it? Does anybody recognize where these pictures are from? Huh? PhD comics, yes. So we take, say, 3 materials. We do computations on them. We analyze the results. By analyzing the results, these are the 2 hard steps. You get some insight into design principles. What I mean by that is you understand why a material has the properties it possesses. Once you understand that, you can then design a new material which has it's the best material to have that property. For example, if you want to make a super, super hard material, you can design it. Or maybe you want to make a very strong magnet, whatever. So now, in the remaining time, I'm going to give you a few examples of work from my group. So how we use DFT to understand the properties of materials. So the first example is, like what I said, can we make a new material? So what is the problem here? So we already talked about bronze, which is an alloy of copper and tin. But you can't just mix any 2 metals and make an alloy. Some metals just don't mix. And there's some rules for when they will mix and when they won't mix. So for example, if you have this metal A and this metal B, and the atomic sizes are too different in the 2 metals, then you cannot make this alloy. It will instead do something called phase segregation. That is, all the A atoms will come to one side and all the B atoms will come to the other side. So people were wondering, is there some way to get around this constraint? And they had this idea of making what's called a strain stabilized surface alloy. So you put only 1 layer of atoms of A and B, and you deposit them on a substrate where the atoms have a size in between that of A and B. Now, people tried to make this, experimentalists tried to make it. In some cases, they were successful. In some cases, it just didn't work at all. So an experimental group in Paris approached us and asked us, can you help us predict? Can you tell us which system we should do our experiments on so that this will work? So I'm not telling you the details of our calculations, but this is my student Madhura. And we predicted that if you take iron and gold atoms and put them on a ruthenium substrate, this will work. Iron and gold don't make alloys in the bulk, but we predicted that it will form this surface alloy. Oops. And this is, do you know what's a scanning tunneling microscope? Yes? Okay, so this is a scanning tunneling microscope image from the experiment. Each of these dark black circles is a single iron atom. And these white things are gold atoms. So each iron atom is surrounded by 6 gold atoms, and this alloy has formed. This is the theoretical simulation of it. This is the experiment. So it formed, okay? But it formed in a structure that we hadn't expected. We hadn't considered it. We just tried some structures. We said it will form. So then we went back and did more calculations. I won't tell you exactly what this is, but just to say we tried lots and lots of structures, and we found that this is the structure that should form, and that's the structure that they indeed found experimentally. Now, why does that structure form? And we found a very unexpected answer, which is that it forms because of magnetism. When an iron atom is surrounded by 6 gold atoms, it acquires a very large magnetic moment, which lowers the energy of the system, and that's why it forms. So this wasn't at all the reasoning behind it when people first looked at surface alloys. So I think this is just a nice example of how you can go back and forth between theory and experiment and theory and experiment. So now I'm going to talk about supported metal nanoparticles or nanoclusters. So this is what's called a catalytic converter. It's there under every conventional car. An electric car won't have it, but a conventional car will have it. And what it actually contains is it will have a ceramic base, like an oxide base, and on that oxide base will be nanoparticles of platinum, palladium, rhodium. These are all actually very, very expensive. Like rhodium is like, I don't know, 10, 20 times as expensive as gold. And what these catalysts do is that the exhaust that comes from your engine, it converts it to less harmful things. For example, an engine produces carbon monoxide, which is toxic, and the catalytic converter converts it to carbon dioxide, which is also bad for the environment, but at least doesn't kill you immediately. Okay? So we want to understand how these things work. So we were looking at gold, and the first thing we asked here is whether we can change the shape of a nanoparticle. Now, when you put these nanoparticles on the oxide, they clump up into a 3-dimensional shape. And we had reason to believe that if you do what is called doping of the oxide, then it will lie flat instead. It will form a planar shape instead of a 3D shape. And so this was the prediction from the calculation that, for example, if you have magnesium oxide as your support, and you replace some of the divalent magnesium by trivalent aluminum, it will become planar. So this was a calculation. This was shown by my student Nisha. And if you have sharp eyes, you would have noticed something about Nisha. Have you noticed something? Yes, her earrings are the two. This is the 2D cluster and this is the 3D cluster. Very well spotted. So this is about why it happens. The aluminum atom donates electrons, which are then transferred to the gold, and then the gold lies flat. I can talk more about it later if you want. And then, of course, the ultimate, I mean, we're physicists. So the ultimate test is always, can you do it in an experiment? Okay, so this is a group in Berlin that did the experiment a few months after we published our paper. They did it on a slightly different system, but the same idea is there. So this is first gold particles deposited on calcium oxide, and again an STM image, and they're forming these 3-dimensional particles. But if you instead dope the oxide, then can you see the difference between the two? Now these are flat, they're like a chapati, and they're only 1 atom thick. So this I thought was, for me, it was extremely exciting that we made a computational prediction and then someone did the experiment and it worked. Okay? So, okay, now comes the part that we're still not that happy with, because the whole idea of it was that we wanted to make a better catalyst. So then we did a calculation, Nisha did the calculation of, is this really a better catalyst? So how do you check? So here we've put these two blue atoms are an oxygen molecule. And you put an oxygen molecule here and try to dissociate it. That is, you try to break the oxygen-oxygen bond. And this graph shows from her calculations how much energy it costs to break that bond as the two oxygens are taken further apart. So this energy here is the dissociation energy. And she found that on this 3D one, it's 0.68 electron volts. On the 2D, it's 0.29. So it is indeed a better catalyst. Now, the part that I'm not so happy about is that since then, people have been trying to do this experiment, and so far they haven't succeeded doing it. We don't think it's because our calculation is wrong. We think it's because they're not able to make perfect materials. They have defects which trap electrons, etc. Okay, so now this is an electron micrograph. This again shows gold nanoparticles on an oxide substrate. Okay, now if you watch when I run the video, you'll see these two gold nanoparticles join up to form another larger one, and these two do too. So can you see the video? You saw those two join? So they move along the surface, that's called diffusion, and then they join up, which is called sintering. Okay, so if you wait long enough, you will see, I don't know if I'll wait that long, let's see a bit. You can see at least they're approaching each other. By the way, every little dot on that is an individual gold atom. Okay, happened. Okay, now this is something we don't want. Why is that? So for example, here this graph shows the diameter of a gold particle versus the rate at which a particular reaction, which is the one I mentioned, which is the oxidation of carbon monoxide, happens. And you see, as the diameter of the particle decreases, the rate goes up a lot. So we really want it to be a nanoparticle. We don't want it to sinter and become larger. Okay? But this happens. Okay? And that degrades the catalyst. So we want to understand how do they do it, when do they do it, are all materials equally likely to do it? So for that, we initially started by studying very small catalysts. So there's a whole field now of what are called single atom catalysts. So here, the catalyst here is just a single platinum atom, which is this blue atom. In this case, they were looking at a particular reaction where methanol is converted to carbon monoxide. I won't go into why. So here, this is again Nisha's work. She's seeing how a single platinum atom moves along a magnesium oxide surface, and this shows how the energy changes as it moves. Okay? Because as you see, when it moves along, you have to break some bonds and make some bonds. And so to break those bonds costs some energy. And so this energy is equal to 0.88 electron volts. Maybe nothing very surprising here, but let's look now at the next larger cluster. It's called the dimer, so it's made of two particle atoms, two platinum atoms. And if you see how it moves, it's quite unexpected. It doesn't just move by translation motion. It does this cartwheeling motion. So we were quite surprised by that. Okay? And now if you have 3, it does this slow walk. And as soon as Nisha showed me this, I said, I know I've seen something walking like that. And it took me a day to figure it out, but this, okay, you know where it's from. Who said Star Wars last time? You don't know this? Okay, so this is a Imperial transport or something. It's called an AT-AT walker in Star Wars. Okay, so I felt it walks like an AT-AT walker. And then if we do 4, oops, I don't know how it went. Okay, it's rolling. Okay, so this was already a surprise to us, and I do have a friend now who's doing experiments, and he thinks he can see all this rolling, etc. And then we found a very surprising thing, which is we found this diffusion barrier energy scales with the bulk melting temperature of the atoms. So let me try to explain to you what I'm saying. So I'm saying that if I have, for example, a metal nanoparticle that is on a surface of a magnesium oxide, I'm looking at the energy it takes for it to move along. And I'm saying that energy scales linearly with the melting temperature of the bulk of that metal, which is kind of quite unexpected. I mean, initially when we told people this result, they didn't believe it at all. They said that's impossible. But then we were able to do more calculations to explain why this happens. And in some cases it fails, and we can also explain why it fails. And we can also see how now it grows from these results. So for example, if you have 4 individual platinum atoms and they form a platinum tetramer, we could study the steps by which it happens. Now, it happens by addition of 1 atom at a time, but in a completely counterintuitive way. What you would think is you'd have a larger nanoparticle, 1 atom would move and join it and form a larger particle. What instead happens is that it's always the larger particle that diffuses and joins the single atom, which is very unexpected. Okay, and for gold, it's different. Okay, so I'm almost done. So the last thing is we've started looking at what are called molecular machines, molecular motors, molecular rotors. So this is an example of a molecule which is inside a cage of other molecules, and it's moving. Okay, so this is the guest molecule, this is the host framework, and this is rotating. So the particular one we studied was this. Now these colors are artificial just to make you see clearly that there are 2 types of molecules here. Actually, so the silver colored ones, if you see, they actually rotate between positions. They kind of switch. Okay, and we were trying to understand that. So this is my student Abhishek, and he did simulations of this, again using DFT. And what you see is that it's rotating. Over here, we've shown how the energies of the system changes as it rotates. These yellow and green blobs are what are called hydrogen atoms between the guest and the host. And what we find is that when the energy is low, there are a lot of these hydrogen bonds. And then when the energy becomes high, like now, there are very few of those hydrogen bonds. So we could understand the energy landscape of this molecular rotor. We could also compute from DFT this energy barrier. They could also measure it experimentally by changing the temperature of the system. And the agreement is almost embarrassingly good. Okay, so what's the take-home message I wanted to give you? It's that first principles techniques can be used successfully for the computational design of novel materials, and they can provide insight into why materials have the properties that they do. I have to tell you also that DFT is always limited by the available hardware. Okay, so we're always pushing at the boundaries. So right now, when I started out my PhD, to simulate bulk silicon took maybe a few days. Now it takes 1 second on a laptop. Some people have even run it on a mobile phone. We can now simulate about thousands of atoms. If we want to simulate a process as a function of time, we can do about 1 femtosecond, which isn't very long. So people are always trying to make better algorithms, and they're also trying to use faster and faster computers. And I haven't at all discussed machine learning, which is something that's totally transforming the field right now. So that's all I wanted to say. Thank you. Questions? Yes.
Ma'am, about the gold nanoparticles that you had showed us, because of their sintering, does it mean that those particles are unstable? That's my first part. And second, through DFT, can we detect the sintering of such nanoparticles?
Yes. So yes, they are unstable. The thing is, nanoparticles are nearly always unstable. The system can always lower its energy by forming a larger nanoparticle. The most stable thing is always the bulk. Okay, so it can always lower its energy. Okay, so certainly you can check that by DFT also. You can calculate the energy of the nanoparticle, the smaller nanoparticle, the larger nanoparticle, the bulk, etc. And you will always find that as the size gets larger and larger and larger, the energy goes down and down and down. Okay, so the question is, how do you prevent it? So you can do what they call protecting the nanoparticle. You put various chemical ligands on it that will prevent it from forming bonds with another nanoparticle. But then if you do that, most of the time, then you lose also the properties you wanted. You lose the reactivity, etc. So this is an ongoing challenge. Anything else? Yes. Okay, so just last week somebody else asked me this. So I don't know enough about astronomy and astrophysics. I haven't seen that. I certainly know people study planetary interiors with DFT, but whether they study stars, I do not know. I mean, what my knowledge of stars is that you have a plasma, and so I don't think you would use these equations, but I don't know enough.
Perhaps in neutron stars, there are other states of matter which could be addressed by this method, right?
Yeah, I guess so. I mean, people even use pre-electron theory for some stars and things, right? So if you add the interactions, I guess you could get a better description. So, but I don't know enough about it.
Me neither.
I meant to look it up, but I didn't get around to it because I gave a talk at TIFR last week. They had this Vigyan Vidushi program, and I was asked exactly the same question.
Ma'am, you mentioned about a molecule where there is an iron and surrounded by gold, right? Could you explain again the reason why it was stable?
Okay, so iron atoms have a magnetic moment. Okay, so if you have a single atom of iron, it has a very high magnetic moment. If you make bulk iron, then there are lots of other iron atoms surrounding each iron atom. And because of what is called hybridization, the magnetic moment becomes less. In fact, in some structures, you lose the magnetic moment completely. Okay? In this particular structure, it so happened that when every ion is surrounded by 6 golds, it retains a very high magnetic moment. And that in turn reduces the energy, what's called the exchange energy of the system, and that makes it very stable. And how we checked that was, this was one of those cases where we redid the calculation without allowing what's called spin polarization. Okay? And then we found that it is no longer that favorable for this structure to form. And so that's how we concluded that it's the magnetism that's playing a really important role in this system.
Hello. Ma'am, can you elaborate more on the planar structure of the gold that was formed? Like
what would you...
the 3D structure, which then later on, due to various simulation, formed a planar structure of gold.
You want to know what the planar structure is, or do you want to know why it forms?
Why it formed?
Okay, so my understanding of it is that when you have, okay, you have magnesium oxide, where the magnesium is divalent. And then you replace some of the magnesiums by trivalent aluminium. So now you have an extra electron in the system. Okay? Now, when you deposit a gold nanoparticle on the system, that extra electron goes to the gold. Okay? And then that charged particle, it can lower its energy. Its energy is lower when it is like this than when it is like that. Okay? And so it has a lower energy. So it forms the 2D shape.
From the energy barrier of a material, what other properties can we predict using DFT?
Okay, so we can predict a huge number of things. We can calculate its structure. We can calculate reaction barriers. We can calculate its elastic properties like hardness and bulk modulus and things like that. We can calculate reaction barriers, as I told you. We can calculate its vibrational properties. We can calculate its optical properties. Pretty much everything, really. Some of them require a bit more sophisticated treatment. So standard density functional theory, which is the sort of the vanilla flavor density functional theory, gives you only ground state properties. And if you want excited state properties, then you have to do something fancier. But we do know now how to do that as well. Now, there's also the other thing, which is, I told you that we have very good guesses for this exchange correlation functional, which is what tells you how to map from the many electron system to the one electron system. There are classes of materials for which this mapping doesn't work very well, and they're called strongly correlated systems. And for strongly correlated systems, DFT doesn't work that well. So some important examples of strongly correlated systems are the high temperature superconductors, for example. But even for these, people are continuously developing better and better theories. And so we can certainly do them much better today than we could a few years ago. But there are limitations.
Ma'am, it was really fascinating knowing about these artificially synthesized molecular routers. So I have two questions regarding these. One is, under what environment are these molecules kept that they behave in this way? And the second one being, what are the chemical properties of these molecules that enable them to behave so?
Okay, so the systems that they're looking at now are very simple ones, and they're studied, I believe, under ultra high vacuum conditions, but at a range of temperatures. The one I showed you is a very simple thing, which just happens to have an energy landscape, a rotational energy landscape, which just under thermal energy, it can rotate. But of course, ultimately, you want something that can be controlled, its motion. Now, I don't know too much about it. Again, I'm not an expert in it, but you may have known that I think 2-3 years ago, the Nobel Prize in chemistry was given for work on molecular machines. So you can look that up, you can see their work. I also know that I think there's a worldwide prize competition for the best molecular car. So, and then of course, again, I'm not a biologist, but a lot of biological processes do involve biological motors moving, etc. So that's a much more sophisticated motion, but that's ultimately what one would like to be able to design and mimic.
So, ma'am, I wanted to ask, with the advent of quantum computers, how will this affect the computation in physics? And moreover, like when quantum computers have been finally realized, would DFT we will be able to use DFT in there, or like what will be the scenario in that case?
Yeah, so this is of course a very good question. And I've been feeling for a while that, I mean, right now the current fashion in DFT is to do everything with machine learning, which I haven't talked about at all today. And I'm guessing that the next big thing will be quantum computation. So there are people working on how to develop quantum algorithms to do DFT calculations. But I think we're a long way from both from developing those algorithms and building quantum computers that are big enough that you can actually do those. So we're not there yet, but I certainly think, I'm guessing it, okay, this is actually a controversial issue, okay? So for example, I'm saying I think it will happen. One of my colleagues who works in a very similar field to me says, this is just hype and it will never happen. So the answer you get will depend on whom you ask.
Ma'am, can you please brief about what are the other fields of physics that uses DFT in research?
So I would say condensed matter physics, all of condensed matter physics uses it. Atomic physics uses it. High energy physics does not use it. What other fields can you think of? Yeah, so astrophysics, I said I didn't know. Molecular physics, you use it. So pretty much all of chemistry, I would say, uses it. Geophysics uses it a lot to study the Earth or other planets or whatever. Chemical engineering uses it. So for example, if you look at the Indian Institute of Science, they have, I think, 8 faculty members doing DFT. One is in physics, one is in solid state chemistry, one is in materials engineering, which used to be called metallurgy before, one is in the materials research center, one is in mechanical engineering, one is in chemical engineering, and I have somehow left out 2. But that's just to give you an idea of the fact that in many fields of science and engineering, one is in computation, and then I've still left out one. But to show that people really use it a lot in many fields of physics and engineering now. Thank you.